Hello, welcome to the course on polymers. In today's lecture, we will try to summarize the overall mechanical response of polymers. We have seen that while in this week 8 we are discussing viscoelasticity of polymers, the response is quite complex. There are several facets of the response, and therefore we adopt various experimental and theoretical means to try to understand viscoelasticity. And not only that, using these means we actually try to get at some of the information which is relevant for applications of these polymers. And so in this lecture we will look at a couple of advanced mechanical properties which are related to fracture and fatigue. And since this is an introductory course on polymers, we will take a brief look at that, and advanced students will have to go and do further studies related to these topics. So, to summarize whatever we have discussed so far, we will quickly look at the phenomenological models that are used for mechanical response, and then we will finish the lecture by looking at failure and fatigue. So, we have discussed phenomena of elasticity, plasticity and viscoelasticity. Viscoelasticity of course is combination of viscous and elastic. So, therefore, from a preliminary analysis point of view and to get handle on how are these different phenomena exhibited by polymers, one could think of polymers as being represented by mechanical analogues, and this is quite similar to electrical circuits analogy. So, we have elements instead of resistors, capacitors and inductors, we have these different mechanical analogues which form, so to speak, a circuit representation of the material. And so, we have a spring element which represents the elasticity in the material. We have the viscous dashpot which represents the dissipation associated with viscous phenomenon, and also we can make a hypothesis of a sliding element. Sliding implies that in plasticity what we saw is there is an yield stress. So, stress goes beyond yield stress, then material starts deforming, and stress remains relatively constant, and but strain keeps on increasing. To represent this kind of behavior, we can use a sliding element which remains stuck until a certain value of stress is reached. Once that value of stress is exceeded, the slider becomes unstuck or slider starts moving, and that implies there is deformation in the material. So, therefore, we can have the viscous dashpot, the elastic springs and a slider element. So, all of these can be used to think of phenomena of mechanical response of polymeric materials. Just cautioning you that these are just representations. We know that at the molecular level and microstructural level, there are far more complicated mechanisms by which a polymeric material responds to loading, stress or strain. So, therefore, these are our way of rationalizing and understanding how the behavior of polymers is. In terms of each of these phenomenon, we can relate it back to the mechanistic details at macromolecular or microstructural scale. For example, elasticity could be related to stretching of macromolecular chains. Sliding could be related to twisting or disentanglement of polymeric chains, and so on. So, therefore, we can correlate many of these phenomena to microstructural details, and this is an exercise we must always continue doing if we have to get a better understanding of the viscoelastic response of polymers. And so, generally these models are useful, and especially in the context of linear viscoelasticity, many of these models are used. For nonlinear deformation of materials, we require much more different machinery, mathematical as well as conceptual, to explain the behavior. However, these are a good starting point in order to understand the material response. So, therefore, the overall model can always be built based on choosing different elements. So, a paint system may incorporate more viscous elements, an elastomer may incorporate more spring-like elements, and so on. And for a semi-crystalline polymer, we may need a combination of all three. So, we can choose depending on the material that we are trying to model and our hypothesis regarding what are the mechanisms in the material. And then after choice of elements, there could be series parallel combinations of these elements. And given that material has multiple processes, we saw there are multiple relaxation processes. So, we may need multiple springs and dashpots to represent multiple relaxation processes. Similarly, there may be couple of yielding phenomena, each associated with a different mechanism, one associated with the amorphous part, one associated with the crystalline part. Then we might have two different sliding elements and so on. And then of course, we have model for each elements. So, this is just like in circuit, we know V is equal to IR for a resistor, and for a capacitor we have an equation, and then when we combine series parallel, we can look at current and voltage across the overall circuit and then simplify it. So, here also for example, we can look at the overall stress and strain. So, if let us say there are these different combinations in parallel, and then you have 1A and 1B and similarly 2, and this is 3A and 3B, we know that stresses. So, when we have series and parallel combinations of these, we know that when they are let us say in parallel, then strain is same in all of them, but when they are in series, then stress is same in all of them. So, using these criteria, we can then try to arrive at what is the relationship between the stress and strain, and of course, these will involve derivatives of stress and derivatives of strain and so on. So, this is as far as overall description of mechanical response is concerned, which is related to deformation in the material and looking at stress strain response and stress as a function of time and strain as a function of time. Over and above this, there are two important features which are very important from practical point of view, are related to failure of the materials. And so, fracture in polymers is basically a phenomenon which happens because there are already defects present in the material, and then we have several molecular mechanisms. Because of the deformation which is being imposed on the material, we can have crazing happening, shear yielding happening, and which leads to micro cracks and voids, and eventually this leads to macro crack, which then can start growing and eventually lead to failure. And so, to analyze the overall fracture, it has been common to look at this from an elastic point of view, because earlier work was done with metals and other structural materials. And the basic idea here is to think in terms of crack which grows, creates a new surface. So, there is a surface energy associated with the crack. On the other hand, there is an elastic material where atoms and molecules are in a minimum energy configuration, and when a crack grows, it basically separates these atoms and molecules. And so, there is an elastic energy which has to be overcome for a crack to proceed. And so, it is a balance of these two sets of energy. So, elastic energy which is related to stress into strain, and so I am sure you can rationalize that this is stress into strain for an Hookean elastic material. And so, that into whatever is the area of the crack, and we will assume for the time being that it is related to unit width, and this is balanced by the surface energy and whatever is the length of the crack. And so, when you do the balance of these, then we can find out a critical stress that is required for crack to be initiated and failure to be observed in material. And this is usually written in terms of this surface energy, or also in terms of GC, which is called the work of fracture, because whenever we create a crack in the material, we are doing work on the material and causing the failure. And so, this is one way to try to find out what may be the stress required for failure in the material given its modulus of elasticity and given the surface energy associated with the cracked surface. And in all of this, the dimension of the cracks are very crucial also. Other way to think about this is also in terms of a stress intensity factor, as we discussed earlier, where because at the crack tip, stresses will be different compared to whatever is applied far away in the sample. So, in general in polymers, given that elasticity is only one type of deformation, there are plastic deformation as well as molecular relaxations and viscoelastic phenomena. We have mechanisms which are different compared to other materials, and in this slide we will just summarize the mechanisms which are there, and all of these mechanisms should be familiar to you, because we have mentioned all of these while discussion related to solid state of polymeric materials. So, in case of glassy polymers which are thermoplastics, we know that there are linear and branched macromolecules which are entangled with each other in the amorphous state, and they also have some amount of molecular flexibility, though exceedingly small, but given the presence of loads, some of these molecular relaxations can take place. And we know that orientation can happen, and because of these processes of relaxation, entanglements and orientation, crazing and shear yielding in the material can happen when material is being deformed. One other feature which is very significant for thermoplastic materials is the phenomenon of crack healing, and this is related very closely with the fact that there are molecular relaxations possible. So, a crack can start growing, but then molecules can start fluctuating back and forth slowly, but eventually heal the crack. So, a crack which was created can also heal itself. On the other hand, glassy polymers which are thermoplastic have a cross-linked network. So, since they have a cross-linked network, the entanglements do not play as big a role here. It is the chain stretching between cross-links which initially is the mechanism by which chains start orienting, and then once the orientation starts happening, you can form fibrils, and therefore crazing can initiate and eventually leading to cracks and failure. But because there is a only chain stretching and crazing happening, the thermosets give us brittle failure. Rubber on the other hand do have cross links, but the chain length is very significant, and because of the segmental flexibility which is present in the case of rubbers, in addition to the processes of cracking and chain scission, there are several segmental motions which can dissipate energy. So, therefore, fracture process is dominated by dissipative mechanisms of viscous nature, which is due to segmental flexibility. The rubbers are quite often used along with fillers. For example, in tire, carbon black is used, and these fillers are usually in the form of agglomerates. So, during fracture of rubber like materials which are filled, there is the additional complication of what are these filler networks doing. Are they agglomerated, or are they getting, the fillers are getting broken up into smaller clusters? How are these macromolecules interacting with these clusters of particles? So, fracture process is far more complicated in case of filled rubbers. And in case of semicrystalline polymers, we have the elastic and plastic deformations of crystal in addition to amorphous chains. And of course, there is orientation of crystals also there. And so, defect mechanisms in the sense that defect move, defect propagation, all of these also contribute to overall fracture phenomena. And lastly, one of the important ways in which we create toughened polymers is by incorporating particles, quite often rubber particles, in otherwise a thermoplastic or a thermoset matrix. And so, these are multi-phase toughened polymers, and in this case, because the rubber particle which is incorporated can deform easily, through particle deformation it can dissipate energy, and therefore, some of the stresses which are there can get dissipated without leading to a crack formation or crack propagation. Similarly, there can be a crack arrested at the interface between a particle and the matrix. So, there are several mechanisms because of which high impact polystyrene or PCABS blends or several such blends where there are rubber particles which are improving the strength as well as impact performance as well as fracture behavior of polymeric materials. So, this is a review related to fracture. Another important mechanism by which materials fail is related to what is called fatigue. And as we know, fatigue is basically getting tired in a usual English sense, and in case of mechanical response of fatigue, what is very crucial here is that we subject the material to loads which are much less compared to the tensile strength. It could be 20-30% of the tensile strength. So, technically material should be able to withstand this kind of a load over very long periods of time. but given that any practical application 20% of load is applied, then it is removed, then it is applied. So, there is a cyclic nature to loading in any given application. Any structural or otherwise automotive or any application you think of, there is always loading unloading going on. So, even if the loads are small, given that there is a periodic loading unloading, material starts responding to that. And so, there is plastic as well as viscoelastic deformations that go on in polymers, and these deformations can slowly start leading to some amount of damage in the material. So, just the way in case of fracture we saw that when load starts reaching closer to the tensile strength or the flexural strength of the material, we have crazing, shear yielding, and then eventually forming a crack. Now, here in this case also, because of the progressive deformation in the material, progressive changes in the material microstructure, crazing, shear yielding and other such phenomena can start taking place. Only thing is they are much more gradual. And so, in case of polymers, because of this plastic and viscoelastic deformation during cyclic loading, fatigue response is observed. What that does is, if you look at, let us say you count the number of cycles to failure. So, we load the stress and keep on changing it as a function of time, and again just reminding you that when we test viscoelasticity of samples, we are in the linear regime where there is no damage at all, where the structure is very close to the equilibrium structure of the material. In this case, by definition, we are subjecting the loads which are much higher than linear viscoelasticity. However, they are much lower than the strength of the material, and even then damage happens because of the fatigue that the material undergoes. And so, the stress amplitude we keep on varying and then measure the number of cycle. Higher the stress we apply, it will fail at much less number of cycles. The larger the number of cycles, it implies that the stress that is applied on the material is much less. And so, therefore, we can see that there is an endurance fatigue limit that we can measure by doing such analysis. In case of polymers, there are a couple of issues which lead to complicated behavior, because there is energy dissipation that can lead to temperature change, and temperature change can change segmental mobility, it can change the mechanisms in terms of disentanglement and so on. So, that has a very strong influence on fatigue behavior of polymers. And because of viscoelastic effect, the frequency of cyclic loading also plays a very important role in case of polymers. So, generally as I said, we can summarize that polymer sample is subjected to a number of cycles at a given amplitude. We measure the number of cycles which lead eventually to failure, and then we look at this response of the curve, and this is a fatigue response, and we can do this for different materials and try to understand why is it some materials fail at much less number of cycles and some other materials which require much larger number of cycles. So, with this we have completed our overall review of the response of polymeric materials. One other thing, for example, we can notice is thermoplastics have lower fatigue resistance because plastic deformation leads to increase in temperature, as was mentioned here, because temperature change strongly influences the fatigue response of polymers. So, in this slide I have tried to summarize the overall set of mechanical response that we have discussed. We can classify them in two important ways: no damage and with damage. In case of no damage, we have elastic response, viscoelasticity or plasticity. In case of elasticity, we have linear elasticity as well as non-linear elasticity. And in case of viscoelasticity, because of our preliminary course, we focused only on linear viscoelasticity. Advanced studies are also there for non-linear viscoelasticity. Plasticity, we have looked at deformation which is accumulated in terms of permanent strain and changes in structure due to orientation, twisting and other mechanisms. So, these are phenomenon which we classify in terms of response of the material. In case of plasticity, structure may undergo some change, and in case of elasticity, the molecular arrangements may change, but they recover back. So, we had a discussion which is not related to damage at all, it is related to response of the material structure to a given mechanical loading. On the other hand, now we have damage. With damage, if we have high rates of loading, then we have basically the impact response, which is significant change in polymer structure. In all of these cases, there is a significant change in polymer structure, including initiation of damage and then growth of this damage in terms of crack growth. Then we looked at fracture, which is also again significant change due to sustained loading, and fracture is where we load the sample up to very high stresses up to strength of the material, and then fatigue, where we load the material to less extent compared to the whatever is the tensile strength. So, with this we close the lecture related to mechanical response and advanced mechanics. I urge you to look at this slide more closely and try to understand and rationalize what are all the different mechanisms by which each phenomenon is different compared to the other phenomenon. So, with this we will close the lecture. Thank you.